Hello everybody, this is again exercise 3.56. We did the mesh analysis beforehand. Now we're going to be doing the nodal analysis for this portion. Same problem, exercise 3.56 from the textbook Engineering Circuit Analysis, 10th edition by William Hayt, and page 82. So now we're going to be doing nodal analysis and just comparing which I think is better for this problem. Sometimes nodal analysis is better for one problem than another. Sometimes mesh analysis is better. So we're just going to be comparing which one is better after we do the nodal analysis. So first thing that we want to do is we want to define our voltages. So nodal analysis, again, if you can recall, is based on KCL. And then mesh analysis is based on KVL. So, but this one's going to be based on KCL, but we need to define our nodes. So first we need to define our ground. This whole node right here is the ground. Next, we're going to define our V's. Since this is already defined as V3, I'm just going to put V3 up here. This is your node V3. This whole node right here, I'm going to call that V2. And then this whole node right here, which I'm just going to put over here, it's called V1. But this V1 is not just this node right here. This encompasses the whole node up here. And so you have, right now you have 3 different nodes, not including the ground. The ground is a node by itself. So we have 3 different nodes that we have defined. And there's no, as we can see, there's no super nodes on this one. So we're just going to go ahead and skip right into the nodal analysis. So first thing that we want to do is a nodal analysis at V1. I like to put nodal KCL at V1. Sorry for my handwriting. Again, I encourage you guys to follow along. If you're gonna, like while watching this video, it might make sense while you're watching it, but once you do it by yourself, like you might get lost. So if you follow by yourself, like, you know, you learn along the way. I find myself learning the best whenever I follow along with what the teacher is doing on the board. And yeah, so let's go ahead and do a nodal KCL at V1. So again, whenever you're doing KCL analysis, you're going to want to define the current going out of the node which equals to the current coming in from any current sources. So what we're going to do is we're going to define the current going out first from the resistors. So it's going to be V1 minus 0, because this is ground. So it's V1 minus 0 divided by 1, which is our resistor. So since this is based on KCL, again, you want to do a sanity check. Voltage over resistance equals current. So this one's based on KCL. The units should match up to and should equal to current, which is amps. So it's V1 minus 0 equals to 1. That's the current going out of the resistors. You're always going to assume the current is going out with nodal analysis, even though that may not be the case at the very end. But right now you're assuming that it's going out. Plus V1 minus 0, again, over this 2 ohm resistors. So it's the current going out of here, the current going out of here, and then the current going out of here. Plus V1 minus V2 divided by 5 ohms. So it's current going out, and then current going out of the 5 ohms. So it's V1 minus V2 over 5 ohms. That equals the current that's coming in from any sources, whether it's the dependent source or an independent source. So in this case, it's an independent source. So it's 25. If this current was going flipped, going that way, then it would be a negative 25. So again, nodal KCL is any currents going out from any of the resistors, out, assuming it's going out. It's probably not the case all the time that it's going to go out, but for nodal analysis, you're always assuming that the current is going out of the resistors, equals the currents coming in from any independent or dependent sources. In this case, since it's coming in, this is going to be positive. And if this is going out, you would put a negative on this 25. So next thing you want to do is multiply everything by a common factor, which is going to be 10. And then again, I like to go step by step. That prevents me from making any mistakes. 5v1 plus 2v1 minus 2v2 equals 250. All right, now we're going to combine like terms. We have 17v1 minus 2v2 equals 250. So I'm going to put a box on that because we're going to need three equations to solve for v1, v2, and v3, and then we'll get to I1 and I2 later. So this is equation number 1. Sorry, apologize. And now we're going to do a nodal KCL at v2. So again, with nodal analysis, you're going to assume the current is going out of the resistors. For now, we're doing a nodal analysis at V2. So it's going to be V2 minus V1 divided by 5 ohms plus V2 minus 0, because that's ground, over 4 ohms plus V2 minus V3 over 4 ohms, and in this case there's not any dependent or independent currents that's coming in, so it's going to equal to 0, and then multiplying everything by a common factor just to simplify it and make it look nice. This is going to be 0, obviously. Over here it's going to be 4v2 minus 4v1 plus 5v2 plus 5v2, sorry, that is a v3, apologize for my handwriting, minus 5v3 equals to 0. And then combining like terms, it was 4v1 plus 14v2 minus 5v3 equals to 0. I'm going to put a box on that one. That's going to be our second equation so that we can solve for v1, v2, and v3. Now we're going to do a nodal KCL. At v3. So the currents coming out of this node is v3 minus v2 over 4 plus v3 minus 0 over 4, 0 because it's the ground and there's no dependent or independent sources coming in or out, so this is going to be 0. And multiplying everything by a common factor, which is 4, you're just going to have v3 minus v2 plus v3 equals 0. And then simplify or combine like terms. And this is going to be our third equation. So now we're going to set up an augmented matrix. Just like to organize everything first. and then we're going to use our calculator to solve these three equations simultaneously. For your first equation, for V1 you have 17, and then negative 2, and then V3 doesn't have anything, so I'll put a 0, and then you have your 250 on the right hand side. For equation number 2, it's negative 4, and then 14, and then negative 5, and then 0. And then for the next equation, it's 0. There's no V1, so the coefficient is 0, and then negative 1, V2, 2, V3, and then 0. We're going to want to solve for V1, V2, V3, and then we'll use V1, V2, and V3 to find I1 and I2 in a few moments. But first we need to solve these three equations. You can solve this by hand, but if your teacher is letting you use a calculator, why wouldn't you use a calculator, right? So let's use a calculator. You could probably solve this by hand, but it might take you a little bit longer. So we're going to edit this, and this is a 3 by 4 matrix, and then we're going to input everything, all the numbers, double checking, make sure everything is good. 17, negative 2, 0, 250. Make sure you want to go slow. If you rush it, you might make a mistake, like I normally do whenever I rush things. So 14, negative 5, 17, negative 2. I'm just double checking. 0, negative 1, 2, and 0. So second, quit. Again, second matrix, go to math, RREF. Second matrix, in this case we use matrix A. So our V1 is 15.33 volts. Watch your units. And then V2 is 5.33 volts, and then V3 is 2.67 volts. And this is one of the things that we wanted, that the textbook was asking the answer for. So we have one of our answers, which is consistent. Sorry, put that up, because V3 is 2.67, which is consistent with our previous answer using mesh analysis, 2.67. So we have that answer. Good to go. Now we need to get I1 and I2. For this problem, I'm going to first find I2. I'm going to get I2 over here, and we're going to use Ohm's law to get I2. And for Ohm's law, I2 is defined as V1 minus V2 equals 5, which is your resistor, times I2. So we know V1, we know V2, and we have I2 as the unknown, so we should be able to solve for I2. And we'll go step by step. V1 minus V2. You could skip easily if you wanted to, but I like showing the steps, especially showing the professor that I know what I'm doing, and maybe you can get partial credit. So V1 equals 15.33, and then 5.33 is V2 divided by 5, which you'll find that I2 is equal to 2 amps. That is one of our answers, which is consistent with our previous analysis using mesh, 2 amps. I2 is 2 amps. Now we need to get I1. To get I1, you can either use, do a KCL using this node over here. And so with the KCL, using KCL, so the node coming in, well, let's draw it first, just to make it clear. Here's your I2, that's known, and that is your 2 ohm. This is your ground. We're going to call this I of Is of 2 ohm, and this is Is of 2. So there's a difference between these two. So now we're going to focus in on this part right here. So we already know I2, and we should know this part right here because this is V sub 1 right here, this node, which we know V sub 1. So we're just going to go step by step though. For KCL, the current coming in is going to be negative I1, and then the current is going out is going to be positive I2 plus positive Is of 2 ohm equals 0. And then we're going to solve for I1. I1 equals I2, which is our known, which is we already know I2, and Is of 2 ohm. And then we can define Is of 2 ohm using Ohm's law. Is of 2 ohm is V1 minus 0, which is the ground, times 2 Is of 2 ohm. And then if you solve for I2, Is of 2 ohm, that's going to equal V1 over 2. So we can plug that in over here. Is of 1, Is of 2, plus V1 over 2. And we already know V1. We got that earlier. It's 15.33 volts. So now we should be able to solve for I1, which we know I2 already. I2 is up here, which is 2 amps, plus V sub 1, which we know, 15.33 divided by 2. And then you'll find that I sub 1 equals 9.67 amps, which is what very consistent with what we got beforehand. So these are your answers. 2.67 for V3, 9.67 for I1, and I2 is 2 amps. And if you go back to our mesh analysis earlier, we have the same answers. So which one do I think is easier? Well, first let's walk through solving this part. For nodal analysis, you had to define V2, V3, V1, V2, and V3, and solve for V1, V2, and V3 using nodal analysis. So we got our equation 1, 2, and 3, and then we plug that in into our augmented matrix using our calculator. We solved for V1, V2, and V3, which gave us one of our answers. But then you had to go another step to get to I2 using Ohm's law, and then you got 2 amps for I2. But then you had to go I1. You had to get I1 using KCL and Ohm's law. So there's more steps, in my opinion, on using nodal analysis for this problem. Is probably going to require more steps than using mesh. And in my opinion, the mesh analysis is probably a little bit easier for this problem, but not by much. So for this one, I think the mesh analysis wins. But it will give us the same answer regardless. All right, thank you for watching.